Hi, I'm Jose Thomas, a computer science student. I've had the incredible opportunity to work with Los Alamos National Laboratory through the Texas A&M ORU program, and I'm excited to present an update to my project. The development of a fourth-generation machine-learned potential with long-range flexible charges for two-dimensional cesium-lead iodide perovskites. This work was made possible by support from the ORU program and by LANL as a whole. I'm especially grateful to my mentors, Dr. Andrews Nicholson and Dr. Robert Stanton, for their guidance and support throughout this project. Now let's start with the basics. What are perovskites? Well, perovskites are a class of materials that follow the general chemical formula ABX3, where A and B are positively charged ions and X is a negatively charged ion, like oxygen or a halide. They form a distinct crystal structure that's highly tunable, meaning its properties can be precisely adjusted by swapping out different elements or modifying the structure at the atomic level. Now, what makes them exciting is their versatility. By swapping different elements into the structure, we can design perovskites for a huge range of applications, from solar cells to quantum computing. In recent years, two-dimensional perovskites have attracted attention for their greater stability, better moisture resistance, and more flexible electronic behavior compared to their 3D counterparts. Our focus is on a specific material, cesium lead iodide, abbreviated CSPBI. This is a halide-based 2D perovskite with strong optoelectronic properties, meaning it responds well to light and electric fields. But while CSPBI is promising, modeling it accurately is extremely challenging. The core issue lies in how most atomic simulation models are built. Nearly all existing interatomic potentials, whether classical force fields or neural network-based models, have been developed specifically for three-dimensional perovskites. These models generally rely on short-range approximations, meaning they only account for atomic interactions within a fixed cutoff distance and ignore everything beyond it. Now that works reasonably well for 3D materials, where the bulk can screen long-range effects, but 2D perovskites, like cesium lead iodide, behave very differently. In 2D perovskites, long-range electrostatic interactions, or Coulombic forces, become dominant. These are the forces between charged particles, like ions and electrons, and they can extend across dozens of atoms, especially in ionic, defect-rich, and strained materials like cesium lead iodide. Under these real-world conditions, strongly localized charge regions develop near vacancies and other defects, creating inhomogeneous electric fields that influence atoms far beyond their immediate neighbors. Conventional short-range machine-learned interatomic potentials, or MLIPs, cannot capture this complexity. As a result, they fail to accurately predict key properties like defect formation energies, charge distribution, and charge transport. Now, to simulate these materials reliably, we need a new generation of machine-learned interatomic potentials, one that captures both short-range chemical interactions and long-range Coulombic forces, while remaining computationally efficient. This is the challenge at the heart of our work. But why machine learning? Well, traditional methods like density functional theory are highly accurate because they solve quantum mechanical equations to model electron behavior, but they're also computationally intensive, scaling poorly with system size, making large-scale or long time-scale simulations impractical. That's where machine-learned interatomic potentials come in. Once trained, they can deliver density functional theory level accuracy while running thousands of times faster. Our goal is to develop a machine-learned interatomic potential that is both charge-aware and long-range capable, bridging the gap between density functional theory accuracy and machine learning efficiency. If we can build this model successfully, it'll open the door to simulating materials like cesium lead iodide with unprecedented speed and accuracy, enabling us to explore how defects form and evolve, how charges flow across interfaces, and how materials respond under stress. These insights are essential for enabling the development of next-generation solar cells, neuromorphic computing systems, quantum technologies, and other cutting-edge applications. Beyond cesium lead iodide, this modeling framework could be adapted to other materials where long-range electrostatics plays a role, such as metal oxides used in catalysis and neuromorphic computing, layered semiconductors like tungsten disulfide, and solid-state electrolytes, essential to next-generation battery technologies. Better modeling in these domains doesn't just improve theory, it can accelerate real-world innovation. At the outset, the plan for this project was to first generate a flexible machine learning model that determines each atom's electronegativity from its local chemical environment, enabling on-the-fly recovery of partial charges. Second, it'll produce a diverse dataset of 2D cesium-lead iodide perovskite configurations representative of the mid to low temperature regime, including point defects. Third, it'll create a charge-neutral, machine-learned interatomic potential for 2D cesium-lead iodide perovskite systems by combining learned electronegativities with a short-range energy force model. To learn per-atom electronegativities, we'll be employing the HIP-NN, the Hierarchically Interacting Particle Neural Network, an in-house deep neural network architecture at LANL. Predicted electronegativities will be fed into a charge equilibration system that enforces overall electroneutrality and assigns partial charges to every atom in a given configuration. Simultaneously, a second HIP-NN network will be trained on total energies and atomic forces from density functional theory reference data to capture short-range bonding and repulsion contributions. To generate representative atomic configurations, simulation toolkits such as Atomic Simulation Environment and PyMatGen will be employed in combination with semi-empirical quantum mechanical methods such as extended tight binding, capturing realistic atomic trajectories and defect structures relevant to 2D cesium-lead iodide perovskites. From these extended tight binding sampled snapshots, a subset of configurations will be selected for higher fidelity density functional theory calculations performed in CP2K to yield total energies, atomic forces, and reference partial charges. Those density functional theory outputs will form the training and validation sets for both the HIP-NN energy force model and the electronegativity predictor. The result will be a scalable, physically informed, machine-learned potential that accounts for both short-range chemical bonding and long-range electrostatics, essential for accurately modeling ionic, defect-prone 2D materials like cesium-lead iodide. Due to issues with the required density functional theory data, we weren't able to reach the implementation stage of the simulations within the limited time frame of the program. Nonetheless, I was fully dedicated to establishing the theoretical and computational foundation required for this project. This involved an in-depth study of the literature on machine-learned interatomic potentials, charge modeling techniques, and the unique physics of 2D perovskite systems. I developed a deep understanding of the HIP-NN, explored the mechanics of charge equilibrium models, and mapped out the complete modeling pipeline needed to integrate these components into a cohesive, charge-aware, machine-learned interatomic potential. As a result, the project is now well positioned for efficient implementation as soon as the necessary dataset becomes available. To prepare for building that pipeline aforementioned, I dedicated significant time to understanding and testing the computational tools that will support it, such as PyMatGen, a Python library used to construct and analyze atomic structures, Atomic Simulation Environment, a toolkit that automates structure generation, manipulation, and simulation workflows, extended tight binding, a semi-empirical quantum method used to efficiently relax structures and generate realistic low-energy configurations. I also worked through how these tools connect to one another in a larger data pipeline, from structure generation to density functional theory refinement, and ultimately to machine learning model training. Looking ahead, the next phase of this project will move from planning to execution. The key milestones are finalizing the density functional theory dataset, training the HIP-NN models for electronegativity and force prediction, validating the model performance on strained and defected cesium-lead iodide configurations, and ultimately using the resulting machine-learned interatomic potential to simulate realistic atomic behavior at scale. The work completed serves as a launch pad for those efforts, and I hope to continue contributing to the next stage of the project. Thank you so much for your time. I'd like to deeply and sincerely thank my mentors, Dr. Anders Nicholson and Dr. Robert Stanton, for all of their insight and support throughout this project, as well as Isabel Cantu and Dr. Michael Demkowitz and the OREU team for making this experience possible. Thank you so much.